Hello children, so these are some NCERT numericals of chapter electromagnetic induction. Let us talk about this. So, what we been asked to determine the direction of induced current. When a wire of irregular shape turns into a circular shape. So, this irregular shape is changed into a circular shape. So, this is first part. Here magnetic field is shown by cross, that is, it is normally inwards towards the floor, vertically inwards. So, see, the irregular wire is changed into circle. So, area increases. Area of circle is maximum for a given length. Area of circle is maximum for a given length. It means when irregular wire is changing into circle, area increases. That means flux increases. Flux is BA, cos theta is 1. Okay, area increases. So flux also increases. Induced current will oppose the cause. है ना? According to Lenz's law, induced current will oppose the cause of its own generation. Oppose the cause of its own generation, that it will oppose the increase in flux. It will oppose the increase in flux. So it will decrease the magnetic field. Induced current will decrease the magnetic field. Given magnetic field is shown by cross. It means induced current will produce a magnetic field towards the roof. So this is the magnetic field that induced current is producing. So keep your right hand thumb like this towards the roof, pointing towards the roof. So curls will give you the direction of induced current. So direction of induced current is anti-clockwise. So answer of first part is anti-clockwise. How to write anti-clockwise? Let us see. It will go as, it was changed into circle. So A to D to C to B, A, D, C, B. So you can write A, D, C, B, A, D, C, B. Let us see the next part of the question. In this part, the circular loop is changed into a narrow straight wire. So this circle is changed into this wire. So when you are going from circle to this narrow wire, area decreases. Flux decreases. Now according to Lenz's law, induced current will oppose the cause. The flux is decreasing, no? Will oppose decrease in flux. So how can you oppose the decrease? By supporting it. So induced current will support the given magnetic field. Then only you can stop it from decreasing. It will support the given magnetic field. Given field is shown by dot. Dot means towards the roof, normally outwards, coming out of the floor. Right. So you will also produce, induced current will also produce a magnetic field in this direction. This is B given, this is B produced. Okay, so according to right hand thumb rule, your curls will you give direction of current, so it is anti-clockwise again. So the direction of induced current is anti-clockwise, and you can see from here the order A dash, D dash, C dash, B dash. And you can write it one more time. Okay, coming to the next question. A long solenoid with 15 turns per centimeter. So number of turns per centimeter is 15. but this is per centimeter. We'll convert into SI unit. So we'll keep 1 by 100 meters. 100 will go up. So it is 1500 turns per meter. This is area of cross section, 2 centimeter square. We'll convert into SI unit. So 1 by 100 into 1 by 100 into the power minus 4 meter square. The current changes from 2 ampere to 4 ampere. So initial current is 2 ampere. Final current is 4 amperes. And time has been given as 0.1 second. We'll have to find out induced voltage. So we know that induced voltage is given by minus d phi by dt according to laws of EMI. Flux can be written as BA, cos theta is 1. Okay, so area outside, it's dB by dt, and B is of solenoid. B is of solenoid, that's mu naught N I. Let us substitute here. So my induced EMF will be equal to minus area d by dt, and in place of B we are putting this thing, mu naught N I. Now take the constants out. Induced EMF will be equal to minus area mu naught N di by dt. This is time which is given in the question, and this is change in current. Di is change in current. Current was changing from 2 ampere to 4 ampere. So 4 minus 2, that is di. This is time. Substitute. Everything is there with you. Area is there. Mu naught. We should know number of turns per unit length is given. Change in current. Yes, we have seen. And time. So you can report your final answer in volts. So let us see the next question. In this, we have to find out what is the EMF and how long does the induced voltage, that is induced EMF, last in each case. So that there are two cases. In first case, the loop, this circular loop, this rectangular loop of metal is being pulled out this way with velocity this. Okay? So we know induced EMF, that is motional EMF with conductor moves in magnetic field, is BLV. You can go through the topic of motional EMF. Formula is BLV. B is this much, substitute. L is the side which is not changing, which is fixed. See, this rectangular loop is making an exit from the magnetic field. It is being pulled this way. So this side will change. It will go out in portions. Yes, slowly with velocity. So which side is not changing is your 8 centimeter. This will change when it will make an exit. 2 centimeter side will change. It will go in portions, है ना? This much portion will go out, then this much. So you'll have to pick a side to be substituted here, which is not changing. So put here 8. This is velocity, substitute. Hence, you can calculate your induced, or you can say motional EMF or voltage in volt. Now coming to how long does it last? That is, time is asked. Time is distance upon speed. Speed is given. What is the distance? Now you will have to write the side which is going out. This is going out. When it will be completely gone, induced EMF will stop. है ना? So this side will be substituted as distance, and the side which is not changing will be substituted as L in motional EMF. Getting to the second part of the question. In second part of the question, you can see it is being pulled like this. normal to the shorter side. Sometimes you have to draw the diagram on our own. So normal to the shorter side is like this and normal to longer side is like this. So first we have to find out motional EMF, which is BLV, V given, B given and L, which is not changing. Now it is making an exit like this. So it will go in portions. So 8 centimeter is changing, but this is complete every time. So what is not changing will come as L. So this side is not changing. So please write that as L to V and B given. Now time, how long the induced EMF lasts. So time is distance upon speed. Which distance will come? Which is changing, which is moving out. This one. This one is moving out. So here will come 8. Upon speed is your 1 centimeter per second. Okay, that will come as 8 seconds. Getting to the next question. Let us go to the next question. A horizontal straight wire of length this. So please note down. Extending east to west. Okay. It falls with a speed of 5 meter per second. At right angles to horizontal component of Earth's magnetic field. So horizontal component of Earth's magnetic field is given as 0.30 into 10 to the power minus 4. It is Weber, it is per meter square, so that is SI unit. So Tesla we can write. First question, what is the instantaneous value of EMF? So conductor is falling, conductor is moving in magnetic field. So instantaneous value of that is EMF will be BLV. Always keep in mind that which B will come, which is perpendicular to the length, to the velocity. Okay? So which B will come? Yes, exactly this only. This magnetic field will come. Here only one is given, that is okay. We understand that one value will come. But whenever two values of magnetic field, three values of magnetic field are given, then always keep here the magnetic field which is perpendicular to L also and V also. So here no choice. So we can substitute directly. Length do we have? Yes. And this also we have. Substitute and calculate. Reported volts. Coming to the next. What is the direction of induced EMF? So yes, it is very important. So direction of induced EMF is reported by Fleming's right hand rule. So we'll use Fleming's right hand rule. Okay, now I'll explain you how to use the rule. See, Earth's magnetic field is south to north. This is Earth's magnetic field. Okay, it is from south to north. Learn the direction. And coming to, it was explained in magnetism too, that Earth's magnetic field is from south to north. Right now you learn it. And coming to wire is falling down. Wire is falling down. So here, see, we are using Fleming's right hand rule. First of all, arrange your right hand. Magnetic field is south to north, as in to the front. Okay? It's not into, it's to the front. So the first finger should be towards, pointing away from you. That is of magnetic field, first finger pointing away, and the wire is falling down. So motion is down towards the floor. Motion means force. Force means thumb. Right hand thumb. Right hand thumb should be towards the floor. First finger should be away from you, south to north. Now tell me, where is second finger pointing in? So when I am arranging like this, I could see my second finger is this way. This is my first finger. Thumb is towards the floor. Thumb towards the floor. First finger this way. And second finger is pointing to this. So what is the direction of induced current? Induced EMF. West to east. Exactly. And that is the answer. After that, we have to see which end of the wire is at higher electrical potential. So if current is flowing from west to east, we know that current flows from higher potential to lower potential. Current flows from higher potential to lower potential. So western end is at higher potential. Getting to the next question now. Let us see the next question. Current in the circuit falls from 5 ampere to 0 ampere. So initial current is 5 ampere, final current is 0, and the time that it takes to fall is 0.1 second as mentioned here. The average EMF is this much. So they have told about EMF already. We'll have to tell about self-inductance. So we know that phi is proportional to I. Phi is equal to Li. This L is your self-inductance and EMF is equal to minus d phi by dt. Let us substitute the value of phi here. So EMF is equal to minus d by dt and phi is Li. Let us take L out. It's di by dt. So final formula that we have is EMF is equal to minus L di by dt. You could have started from here also. If somebody knows the formula, you can start. So EMF is this. L is to be found. Change in current you can find out. Bigger minus smaller. Or final minus initial, that is okay. And time is given. Substitute here. Change in current here. That's all for to find out self-inductance in Henry. Let us see question number next. A pair of adjacent coils has a mutual inductance of 1.5 Henry. So mutual inductance has been given as 1.5 Henry and current changes from 0 to 20. So this is initial current 0 and final current is 20 ampere. Time is given as 0.5 seconds. What is the change of flux linkage with other coils? So that is okay. See, we will be writing two formulas of EMF. One is this and one is when we write flux is proportional to I. See, here is a concept of mutual inductance. So you can simply write like this. So it is equal to constant is mutual inductance of second coil. But now we know that mutual inductance of both the coils are equal. So we don't need to use the same symbol as in derivation. Okay, now we know that it's same. Okay, so let us substitute this here. If you wish to do it without symbol, you can do it without symbol as well. So if you wish to use symbols, then it can be like this. So let us substitute phi 2 here. So E2 is equal to minus d by dt and it is M I1. I1 is in current in 1. So initial current you can denote by II and this is final current IF. So do not get confused that I1 is the initial current. No. So M outside. Both the M outside and D I1 by dt. Now this formula and this formula can be equated. Let us equate. So minus d phi by dt is equal to this M di by dt without symbols I'm writing. So dt cancelled. So change in flux can be obtained. Change in flux, mutual inductance have been given, and change in current, you know, final current minus initial current. Change in current, you know, mutual inductance is given, and change in flux can be reported. That is a question. Find out change in flux. So let us go to the next question. So what I've done here in this question, I have taken two formulas for EMF and I've just equated them. this is directly proportional to I, this is equal to mi. So m outside di by dt. That's all. This is what I've done. Getting to question number 10. Speed is given of jet plane. So very important question. Let us understand it properly. Velocity has been given as 1800 km per hour. Change into meter per second. Do it. Because we have multiplied it with 5 by 18, so it will change into meter per second. Please convert. What is the voltage difference mean? Induced EMF is asked. Length of the wire is given. Length of the plane is given. Earth's magnetic field at that location is, so this is Earth's net magnetic field 5 into 10 to the power minus 4 Tesla. Angle of dip is 30 degree. Now look, the plane is traveling west. Plane is traveling to west in air, obviously. Now see, Earth has two magnetic fields, BH, horizontal component and vertical component. Now which is normal to it, we will be using that. This is on Earth. Horizontal component is on Earth. In air, this is there, vertical component. It is like rain. So whatever I've said, please listen to my wordings again and again. Earth has two magnetic fields, this horizontal, which runs from south to north on Earth. This is in air. On Earth, close to Earth, we will write horizontal. और ये air में होता है vertical, and it is like rain. Downward or upward. But I'm just telling you vertically downwards or upward. Okay. So which lines will cut it normally? Vertical magnetic field. So we'll have to find out vertical magnetic field. You know it is B sine delta. B is given. 30 delta is given. Substitute. You'll get this in Tesla. And now we have to find out motional EMF. B. Which B will come? This, which is normal to the conductor. Vertical component of Earth's magnetic field. Length is given. Velocity is given. Other things, no problem. So this is how we can find out the voltage difference. Let us get to the next question. This is area, number of turns. So area given, number of turns given. Okay, but there is a coil which has been snatched out of the magnetic field. Field normal है, so best. Will have the total charge flown in the coil is this. So charge is also given. When you were snatching the coil out of the magnetic field, this much charge has flown, obviously due to the induced current. So you can convert this into 7.5 milli is 10 to the power minus 3 coulomb. Otherwise, everything you take in SI units. This is 2 into 10 to the power minus 4 meter square. Okay, the resistance of the coil is, yeah, galvanometer is, galvanometer and coil both is this 0.50 ohm. We'll have to find out the magnetic field strength. Field strength is to be calculated. So what do we know? That there was a coil which was this coil which was snatched, taken out of the magnetic field. So obviously conductor moved in magnetic field, so it is equal to. Now see, what have they talked about? We'll have to see according to that. So here we have number of turns and area and charge. They are talking about. Resistance is also there. So let us use a basic formula. It is equal to d phi by dt. So flux can be written as, if you wish to use negative sign, you can use. Flux can be written as BA. Okay, area can be taken out as dB by dt. So my EMF is ready as minus area, because they talked about find out magnetic field. So yes, so area dB by dt. dB can be written as like final magnetic field minus initial magnetic field, and this is time taken. Okay, now how much is the final magnetic field? 0, because you have snatched a coil out of magnetic field, so there is no final magnetic field, it has gone out, so it is 0. Initial magnetic field is to be found, and this is time. Okay, so this is EMF. Now one very important thing, they have given n number of turns, so we have to multiply this with n. Be very particular, minus minus plus, n has to be multiplied. Now what is this? This E is voltage, induced voltage. So voltage can be written as I into R. Simple. NAB by T. And current can be written as charge by time. NAB by time. Time cancel. So magnetic field can be calculated as Q into R upon N into A. And everything we have, charge flown, resistance, number of turns, and area. So here the coil was snatched, whichever area it was snatched out of the magnetic field. Final magnetic field was 0. Initial was given. Conductor was moved. Why didn't I use BLV? Because there is no mention of velocity, no mention of L. So avoid that. You don't have those particulars. And now what we have is number of turns. So we'll use basic formula. Pi was open as BA. A out dB by dt. dB is change in magnetic field. B2 minus B1. Final magnetic field is 0. This is voltage. Voltage can be opened as current into resistance IR. I can be opened as this. That's all. Substitute and calculate in Tesla. So children, practice these numericals. Rest of the numericals I will include in next video.